Good morning, everyone. Today we will discuss another experiment that is velocity of sound in air by using resonance apparatus or resonance method. So, the objectives of this session, after completion of this session, a student is able to adjust the reservoir level and finds the first and second resonating lengths and calculates the velocity of sound at 0 degree Celsius. Here he or she is able to arrange the apparatus and he adjusts the reservoir level and finds the first and second resonating lengths, and he calculates. Student is able to calculate the velocity of sound at room temperature and at the temperature of 0 degree Celsius. For this, here we have to once recall some of the definitions or terms involved in this experiment are the frequency. The frequency is the number of vibrations made by tuning fork flange per second are called as a frequency, or the number of vibrations made per second is a frequency. Here frequency is measured in hertz. Next one is the resonance. This is a phenomena. The resonance is a phenomenon in which the frequency of an applied periodic force is equal to the natural frequency of the body, and the body starts vibrating with maximum amplitude. This phenomenon is called as a resonance. And end correction. The distance between the open end of the tube and the actual formation of antinode is called as a end correction. Here you can see the end correction here. Actual node here. This is the end correction. You can see this. This is the end correction, or this is the end correction. So here the resonance apparatus. Velocity of sound in air by using resonance apparatus. This is the resonance apparatus we are using in our laboratory. So the apparatus consists a glass tube, or it is a metal tube. If metal tube is there, then a small normal pipe, transparent pipe is attached here to the tube and the reservoir. The 1 meter length of this tube, so it is a steel pipe or a glass tube, and the diameter about a 4 centimeter. This is fixed. This apparatus is fixed. This apparatus is fixed on a vertical wooden stand. The lower end of the tube or pipe is attached to the reservoir by means of a rubber tube. This is the reservoir. This is a rubber tube attached, and a meter scale is fixed by the side of this pipe. The meter scale is shown here. This is fixed side of the pipe or tube. Then you can measure easily the readings. The reservoir can be raised up and down. This reservoir can be moved up and down by using a screw, and it can be fixed at any position. This is a resonance apparatus. Resonance apparatus, it consists a 1 meter long and nearly about 4 centimeter diameter pipe of steel or glass. It is fixed vertically on a wooden stand. The lower end of the glass tube is attached to the reservoir. This is made up of steel here. By using a rubber tube, a meter scale is fixed to the side of this pipe, and the reservoir can be moved upside or downside, lower side, and can be fixed it at any position. That is the resonance apparatus. So by using this resonance apparatus, we have to find out the sound velocity in air. So aim of this experiment is to determine the velocity of sound at room temperature and at the 0°C temperature using resonance air column apparatus. And by using this experiment apparatus, you can compare the frequencies of a given tuning forks. If the two tuning forks are given to you and you are able to compare the two frequencies of the tuning fork, and you can determine the unknown frequency of the given tuning fork. By using this resonance apparatus, we can find out the velocity of sound in air. We can compare the frequencies of the given two tuning forks, and we can determine the frequency of the given tuning fork. Here the apparatus we required is a resonance apparatus, a tuning fork, and a rubber hammer. The rubber hammer is used to vibrate the tuning fork, and water. Resonance apparatus, tuning fork, rubber hammer, water. Tuning forks with different frequencies are needed. Here the principle or theory, this resonance apparatus works on the principle of resonance in air column of the closed organ pipe. Resonance in a closed organ pipe is a principle of this resonance apparatus. For example, this is a pipe. Here up to this condition water is there. So now this is a closed one, closed with other end is closed, one end is open. So resonance apparatus works on the principle of resonance in air. Here this up to this air is there, right? This is air and this is water. This is a water. So the resonance in the air this is a water, this is air, right? So resonance occurs in air column in a closed pipe. How it occurs? Based on that principle, this apparatus works. So here you have to find out the temperature of a room. How much temperature is there in the room? So let the L1 and L2 are the first and second resonating lengths. L1 and L2 are the first and second resonating lengths. Here, see this, up to this water, the first resonating length, say this is the L1 and this is the L2, first and second resonating lengths. Then N is the frequency of a tuning fork which is vibrating. Then the velocity of the sound at room temperature can be determined by the formula V T equals to, or V equals to or V equals to 2n into L2 minus L1. So you can write it Vt equals to 2n into L2 minus L1, where L1 is the first resonating length and L2 is the second resonating length. So from this equation, the relation of the velocity of sound at 0 degree Celsius is V0 equals to Vt into 1 minus T by 546. From this relation, you can find out the velocity at 0 degree Celsius, where T is the temperature, room temperature at room. In the room, what is the temperature? That shows this T, and Vt is the velocity of sound at a room temperature. So by using this temperature and velocity of sound at room temperature, you can find out the velocity of sound in air at a 0 degree Celsius. So here here we have the procedure. The procedure is, first fill the apparatus. The apparatus is filled. The apparatus, that is the pipe, resonating pipe, or the main pipe of iron or steel. This one, this pipe is filled with water, and the reservoir is raised to upward. First, initially make sure that the resonance apparatus should be vertically placed, and take the reservoir to top of the stand. The apparatus main pipe and the reservoir should be at a same level. Upper level should be same. Now fill the reservoir with water. Pour the water into the reservoir, then water goes to the main pipe. So the reservoir, as the pipe fills, you can see the reservoir level, water level in a pipe by using a transparent plastic tube, which is connected in between the reservoir and the main pipe and a reservoir, and it is fixed on the scale. So now the completely filled, and the reservoir is raised to upwards, so that the main tube is completely filled with the water. So now take a tuning fork and first vibrate it and observe the vibration sound. This is to identify the sound produced by the is without confusion you can get the raised sounds made by the vibrating tuning fork. So the sounds, if you listen initially, then it helps to helps as a reference to understand whether the sound is coming or not. So now take the tuning fork of frequency, take it as N and note down the frequency, and it is excited with a rubber hammer. Vibrate the tuning fork with the rubber hammer and held this tuning fork above the open end of the iron tube or the main tube. The reservoir is slowly lowered, slowly goes down until a large booming sound is heard. So whatever the sound you heard by simple listening vibrating tuning fork, that type of a sound you can heard loudly. So the reservoir is fixed at that position. The reservoir is fixed where the large booming sound is heard, and take the length of the air column is noted. The air column length is noted. Here now see the observe this here reservoir is lowered, so the water level decreases. Now put a vibrating tuning fork at the above to the open end of the pipe. Then at some level the reservoir is going down, so the water level decreases. Then you can hear a resonating sound. So this now you fix the reservoir at that position and make note the length of the air column. So this length of the air column, the distance from open end of the pipe to water level where you heard a booming sound, large sound is heard. Make note it the reading where at what length you got this sound, and the experiment is repeat again with the same frequency for two lengths. L1 experiment is repeated, and you have to take the two lengths and then calculate to get the average length for accuracy. So keeping the same excited tuning fork above the open end of this tube, the reservoir is further lowered. Take it down, so it is lowered until a large booming sound is heard again for the second time. So first at for example, you heard the first sound at this length. Now you take this reservoir down, so water level decreases, then you can heard another length. Say this is a L1 and this one is a L2. The second time you heard a large sound, this you have to repeat the same experiment. Vibrate the tuning fork and held it on the top of the open pipe. Then you can heard a larger sound then you make the note where the L2 or second length is at, you have to note down the second length value. So whether, for example, if the first length occurs at the 16, then second length will be approximately near to the 48, because it is observed that the L2 second length is slightly greater than the 3 into L1. 3 into L1. So you have to go down, lower the reservoir, then you get the second near to the 3 times of the first tone, first length, 3 times of the first booming sound you can heard, that is L2. This experiment is repeated with 2 more tuning forks of different frequencies, and the resonating lengths L1 and L2 are noted. The values are tabulated. These values are tabulated in this table. The velocity of sound at room temperature can be calculated by using the formula Vt equals to 2n into L2 minus L1. Taking the average of these, you can find out the velocity of sound at 0 degree temperature. This is the procedure you have to follow to get the L1 and L2. So for getting L1 and L2, for this experiment, L1 and L2 are the two lengths. So first take in the tabular form, you have to take that first frequency, for example 284. So first length is 18 and second time 18.2 and mean is 18.1 and trial to 57, 58, 57.5. Now you can calculate this Vt using 2 into n, right? So you have to tabulate all the readings and you have to calculate by using these readings. First you take the readings of trial 1 and trial 2 and mean L1 first resonance and second resonance, then your experimental performing of experiment by using resonance apparatus is over, then you can calculate by using your calculators or by your own. So now you take the, you need to know the values of here, you know the values of L1 first resonance, L1 and L2 and n value, you know the three values. Then what is the formula for this? Vt equals to Vt equals to 2n into L2 minus L1. So T is a room temperature, L2 is a second resonating length, L1 is a first resonating length and n is the frequency. So calculate all these. Here by using this formula you can calculate Vt and you will get different Vt's, then total it, then take the average of this total by number of times, 3 times I am taking the number of times. So now you will get a average Vt value, average velocity at room temperature. For example, that is 3010 31,080 centimeter per second is the, for example, that is the room temperature. So room temperature is taken as 28. Now the room temperature is 28 degrees Celsius. Then you can find out this value. You can find out this velocity of sound at 0 degrees temperature by using Vt V0 equals to Vt into 1 minus T by 546. By using this formula, you can find out the velocity of sound at 0 degrees Celsius. So what is the average? Here the observations are, what is the average velocity of room temperature? The room temperature is observed as a 28 degrees Celsius. For example, average velocity at room temperature is observed as a calculated as a 31,080 centimeter per second, and now you should substitute this value. For example, the V0 equals to Vt is 31,080 into 1 minus 28 by 546. So you will get some value that is for example 29,000 something. That value is a velocity of sound in air at a 0 degrees Celsius. So these are the observations, and tabular form you have to make note the readings, and you must take the precautions. So here we have some relations between the velocity and temperature. So the velocity of sound in air is directly proportional to the square root of the temperature of the medium. Here, why we are taking this value at temperature means the sound velocity in air is directly proportional to the square root of the temperature, absolute temperature of the medium. Here we are using the medium is the air, so air temperature, and the velocity of sound in air is inversely proportional to the root of 1 by d square, 1 by d. The velocity of sound is inversely proportional to the square root of the density of the medium, and the velocity of sound is independent of the pressure of the medium. Independent of the pressure of the independent on pressure. These are the factors influences, or these are the factors the velocity of sound in air depends. It is independent of pressure. It is directly proportional to the root of absolute temperature of the medium, and inversely proportional to the square of the density of the medium. These are the factors which affects or which depends, sound velocities depends on these factors. So if what happens if the frequency of a tuning fork or a tuning fork piece of wax is attached to the flanges of tuning fork. Then the frequency is decreases due to the increase of mass. Increase of mass, the frequency decreases. If you fill the two tuning fork flanges with some material, then what happens to the frequency? Here it is filled. So the frequency is increases due to the decrease of the mass, right? So here these are the factors, and these are the situations. If the tuning fork is changed or waxed, or the inner place is filled, then the frequency changes, right? So now you have to take precautions. The precautions must be followed because to get the accurate value. So resonance tube must be vertical. It should be vertical, clearly vertical. It should not like this. It should not be like this. It should be like this, exactly vertical. The excited tuning fork. So vibrating tuning fork or excited tuning fork should be held with its flanges are horizontal, and they should vibrate vertically along the axis of the tube. So it should be, the excited tuning fork must be held with its flanges are horizontal, and for example this is a open area, so the tuning fork must like this. So its vibrations should vertically goes down. Otherwise vibrations does not go vertically. They incidents on a sides of a pipe. That leads to we won't get any louder resonating sound. Now the tuning fork of a longer frequency should be used at the beginning. At the beginning, the longer frequency should be used. The tuning fork should be excited gently with the rubber hammer. Don't vibrate it very hardly. You have to vibrate tuning fork gently. And the flanges of tuning fork should not be touched with the hands while they are vibrating. Don't touch the tuning fork vibrations, otherwise its frequency changes. And the length 1 and length 2 should be noted exactly without parallax. In general, the second resonating length is greater than the first resonating length 3 times of the first resonating length. So these are the precautions you should follow while performing the experiment. And then the errors occurs. How the errors occurs then in this experiment? So first, resonating tube or resonance tube may not be vertical. If the resonating tube is not exactly vertical, then you will get a wrong answers or errors. And in the air column is denser than the open air outside. The density of the inner air in the air column is more than the outside air, this also reduces the velocity of sound slightly, because the inner density is more, though automatically the velocity of the sound decreases. If air in the air column has humidity, it increases the velocity. If the humidity is more in the inside the air column, then it increases the velocity. So these are the errors occurs, and if you don't put the vibrating tuning fork exactly horizontal to the uh, pipe open area or top of the pipe, then also errors occurs. If you touch the tuning fork flanges when they are vibrating, then also errors occurs. If you are touching the open air pipe, resonating pipe with the tuning fork, then also errors occurs. So these, to eliminate these errors, to reduce these errors, you have to follow all the precautions exactly. Then you are able to uh, decrease the errors, or you can minimize the errors. Then finally, the result. So what is the result here? So result is, you can write this Vt equals to so and so, V0 equals to something, centimeter per second and centimeter per second. So these are the results you have to write. The velocity of sound in air at room temperature, Vt equals to something, 31,120 something, whatever the value you got. And another one is velocity of sound in air at 0 degree Celsius temperature. So these are the results you have to write. So if he asks for the results, find the frequency of a given tuning fork, then you have to write the frequency of a given tuning fork. It is founded as frequency third frequency f equals to something hertz, right? And another tuning fork. If two tuning forks are given, then you can write it as like how he asks. So you can see here the whatever the, if the ask for the compare the two frequencies. Now the different questions rises based on this. So determine the velocity of sound in air at room temperature and determine the velocity of sound at 0 degree Celsius are discussed here. And if he asks for the compare the two frequencies, if asked for the compare the two frequencies, then what is the procedure? So if the given two frequencies are unknown frequencies, now take it as a N1 excited with a rubber hammer and held above the open end of the pipe. Now follow the same procedure. The reservoir is slowly lowered down until a large booming sound is heard. The reservoir is fixed at that position where you heard a large booming sound, then that is the length of the air column is noted here. So experiment is repeated again, and you have to take the two lengths average of the two air column length, that is L1, is calculated. Now keeping the same excited tuning fork above the open end of the tube, the reservoir is further lowered. The same procedure. The procedure is same until the large booming sound. Now also large booming sound is heard again at the second time. The large length of the second column, air column, is noted. So here you have to note down the first length and second length of air columns. The experiment repeated with the second tuning fork for unknown frequency N2. So actually the tuning fork frequency is noted on a frequency, but this number is covered with plaster or anything you will given. So now you have to find out the unknown frequency. So now repeat this frequency, the same experiment with the second tuning fork, and find out the first length and second length of the air column. Now the ratios of frequencies is determined by using N1 by N2. If the first frequency is first tuning fork is N1 and second tuning fork is N2, then L2 minus L1 by L2 prime minus L1. So here L1 and L2 are taken as the first frequency for first tuning fork's lengths, and L2 prime and L1 prime is taken as the second tuning fork air column lengths. So by using this N1 by N2 equals to L2 minus L1 by L2 minus L1 of a second tuning fork, you can compare the two tuning forks. So another question will rise is, they determine the frequency of a given tuning fork. The tuning fork determine the frequency of the given tuning fork. One tuning fork frequency you have to find out, it is unknown. Another one is given known, or simply unknown tuning fork is given and you have to find out the frequency of the given tuning fork. So here the same experiment you have to do with the given frequency given tuning fork, which is unknown to you. Now here in this tabular form, the frequency is unknown, that's why you can take it as N. The frequency is taken as N. Now perform the same experiment for the two times. You will heard a booming sound. Take note, it's a L1, and repeat the experiment and take the L1 first length second time and take the average of these two. Then you will get a first resonating length. So now you take the same, repeat the experiment by lowering the reservoir. You will get a second tone, second resonating length. You have to note the second resonating length and repeat the experiment, take second time and take the average of these two, first and second time. Then you will get a second resonating length. By using these resonating lengths, you have the formula here. The formula is Vt equals to 2n into L2 minus L1. Here the Vt is given. If the examiner asks to find out the frequency, then he will give the sound velocity. For example, here the sound velocity is given v0 is 330, vt is given as a 330 meter per second. So now you have to substitute this value at this vt value, and you have to find out this n. So you know the values of L2 and L1. You know the values of L2 and L1. So Vt is given value from this 2n L2 minus L1. So n equals to Vt by 2 into L2 minus L1. By using this formula, you can find out the unknown frequency of a given tuning fork. So by using this resonating apparatus, you can find out the sound velocity in air at room temperature. By that, you can find out the velocity of sound at 0 degree cell temperature, and you can compare the two unknown frequencies, and you can find out the unknown frequencies of any number of given frequencies. So this is the use of the resonating apparatus. These are the questions rises based on this resonating apparatus. So once again, I am remembering what you have to write in the examination. So first you have to write the aim, and the same should be reflected in the result column. If the question is determine the velocity of sound in air at 0 degree Celsius using resonance apparatus, then your result should be the velocity of sound in air at 0 degree Celsius is equals to something in and its units. And apparatus, what are the required apparatus? Even though you have to write the water also, some of the students are writing the resonance apparatus, tuning fork, rubber hammer, and they are forgetting the writing the water. Without water, how can you perform the experiment? The apparatus is ready, but you require the water also. That is important. And you have to write the principle or theory, then the procedure, then you have to draw the tabular form, and you have to do the calculations, and you must write the precautions and then results. So without precautions, your experiment is not complete, because if you are not following any precaution, it leads to the damage or leads to different effects, negative effects. Negative impact will be there while performing the experiment if you are not following the precautions. So this is the experiment procedure and the objectives of the experiment of a resonance apparatus. So by this resonance apparatus, you can from this resonance apparatus you will get a 3 or 4 questions, but each question comes to only one student. So you have to perform only one experiment without eliminating or without leaving any point. Aim, apparatus, theory, procedure, table, precautions, graph, errors, right? After that, you will have an viva based on theoretical knowledge on the experiment. Okay, thank you.